Hi, my name is Rory O'Connor. I'm a rangeland ecologist for the USDA Agriculture Research Service. The title of my talk is Sage Steppe Carbon Dynamics in the Great Basin. This project is in collaboration with the Nature Conservancy and Oregon State University. I'm going to begin my talk by talking about general rangeland carbon dynamics. I'll then go into how we should look at carbon dynamics in the sagebrush steppe. What do we know about these carbon dynamics in the sage steppe based off of literature review and synthesis? What data are we missing from the Great Basin? And then conclusions that are generalizable across rangelands. For rangeland carbon dynamics, a lot of focus has been on grazing. And the research has turned up that grazing has little to no effect on soil carbon pools of rangeland soils. Mesic rangeland grazing does increase reproduction, which increases carbon in the upper soil layers, but not throughout the entire soil profile, causing little to no increase in carbon. However, chronic inappropriate grazing does decrease substantially carbon inputs into the soil profile. Rangeland carbon fluctuates between sink and source each year based on precipitation, soil moisture, and disturbance. But in general, most rangelands are carbon sink, and the strength of that sink is dictated by those same processes, abiotic and biotic. So how do we look at sage steppe carbon? Well, we need to use simplicity and to generalize rangelands at their current ecological state. And in using the threat-based Manager's Guide to the Northern Great Basin, they identified 5 main ecological states that occur in the Great Basin. The first is a native shrubland. So here in picture 1, we have our native shrubland. It's a sagebrush dominated site with perennial bunch grasses. The second is a perennial grassland. So you can see here in figure 2, where you have your site dominated by perennial bunch grasses. And this can be native or crested wheatgrass. And I'll get into this further on in my talk, why we should look at both. We have our degraded shrubland with annual grasses. So we have our sagebrush with a bunch of annual grasses as the understory. We have our annual grassland, could be cheatgrass or medusa head or ventonata, and we have our juniper woodland, which has a whole suite of understories from no understory to perennial grass and sagebrush. So using those 5 main ecological state types, we did a literature review of peer-reviewed sources, and we looked at all the different general search terms for carbon dynamics: carbon, biomass, litter, organic, soil, and we searched by specific species. So the main species of those ecological states. So we have sagebrush, we use mountain, basin, and Wyoming. We have crested wheatgrass as one of the perennial grasses. We have cheatgrass, medusa head, ventonata, and we have juniper, both western, Utah, and Rocky Mountain. And all of these came up with about 3,000 articles. The breakdown of how many articles each search populated shows up here in bold letters or in bold numbers. And there is some crossover, and those are currently being removed for a total number. But so far, this is what we've come up with. And the results we've found has been with sagebrush, we have roughly 55 teragrams of carbon across the entirety of the Great Basin. We see a big elevational and latitudinal, as well as longitudinal gradient of biomass for sagebrush carbon dynamics. We can see that in our more mesic areas, we have 440 grams of carbon per meter squared, whereas in the more arid areas, we have 89.4 grams of carbon per meter squared. And you see the same pattern of more at the wetter sites, lower values at the drier sites. And to remind you, these values are not final. The synthesis is ongoing, but we are seeing this is about the range that we've found thus far in the papers for the data. When we look at our perennial grasslands, very little research has shown biomass and soil organic carbon at these sites that it's perennial grass dominated. where you have less than 10% sagebrush cover. There are a few, but what we found at some sites where crested wheatgrass has been present is you get about 1.3 megagrams of carbon per hectare for above ground biomass. And all of these values have been scaled up for the Great Basin based off of a master's thesis from Boise State. And we see that we do lose some carbon above ground from your sagebrush steppe, but overall we do keep a lot of carbon below ground, and that is the point of having perennial grasses on the landscape, is to introduce carbon into the soil profile through the fine root turnover and root exudates. In degraded sagebrush sites, we lose even more carbon. If you remember, we had 89 to 400 grams of carbon per meter squared. With a degraded sagebrush site, we have roughly 130 grams of carbon per meter squared, 138 grams of carbon per meter squared, and our below ground biomass decreases substantially. And that is because we're losing all those perennial grasses and a lot of the above ground biomass from sagebrush. If we further degrade the site to an invasive annual grass site, we lose overall what's been estimated overall 2 billion metric tons of carbon across the Great Basin if it's converted to cheatgrass. That hasn't happened yet. It's if it converts to cheatgrass. But as you can see, above ground biomass is roughly 39.8 grams of carbon per meter squared, which is 200 to 400 grams of carbon less than a native perennial grass site, or less than a native sagebrush perennial grass dominated site. And so overall, we essentially lose 50% of our stored carbon through conversion to cheatgrass dominated systems, if not more, which is extremely problematic for future restoration and for storing carbon in our soils. If we look at it, juniper encroachment, we gain a ton of carbon. We gain 129.1 teragrams of carbon, which is 70 to 80 teragrams carbon more than sagebrush sites. And the reason there's more carbon is because it's found in above ground carbon stocks. There's very little below ground root carbon present compared to the sagebrush steppe sagebrush sites with perennial grasses, but most of this is all above ground biomass. And the reason why that matters is if a fire comes through, all of that stored carbon is then lost and volatilized into the air. The remaining timber that's left on the ground will eventually decompose into the soil, but it will take decades, if not a century, for some of these sites to reincorporate that carbon. And these sites will further transition into more degraded areas, which is problematic. So based off of the literature, where are our research needs? Well, we need to sample soil organic carbon in the deeper soil profile below 30 centimeters. We need to look at below ground root biomass and understand fine root versus coarse root, microbial respiration and heterotrophic respiration in those profiles. We need to look at carbon flux data across annual grasslands, across degraded grasslands and woodlands. We need to look at the other invasive annual grasses and how they're changing carbon dynamics with Medusa head and ventonata. And we need to incorporate repeated measurements on our landscape. We need to go back year after year, sometimes 5 years, wait 5 years, 10 years, 15 years to go back and sample soil organic carbon and root biomass to see how the landscape has changed based off of the ecological state. So what are our conclusions? Well, we found that we need to manage landscapes for fire with all available tools. We need to understand how annual grasslands, degraded shrublands and woodlands, how they react with fire and how they transition out of those states into different ecological states. Adding more trees to the landscape does not increase rangeland carbon. In fact, it has the potential to decrease rangeland carbon. If a fire does go through it will transition out of a woodland into a degraded rangeland, which will release more carbon over time. Livestock grazing is not the silver bullet for carbon sequestration. Livestock grazing is a tool, and we should use it as such, but we should not be reliant on it for sequestering more carbon on our rangelands. And we need to take the long view for rangeland carbon. We need to create management plans that are more than a few years down the road. We need to look at decades down the road for our management. So thank you for listening. If you have questions or comments, my contact information is down here at the bottom of the slide. Please be aware that my last name has an apostrophe, so it's rory.o'connor@usda.gov, and the apostrophe is after the O in O'Connor. Thank you and have a good annual meeting.